Now that we have some concrete examples of representations, we work more abstractly. So the theme is, how do we construct new representations from old ones? Here, we'll review the major constructions from linear algebra, and we'll see where representation theory fits in. Now, recall, we have G a finite group. Pi v, pi prime v prime are going to be finite dimensional representations of G over the complex numbers. For our first construction, we have external direct sum. Now, we've already seen internal direct sum when we've decomposed examples into irreducibles. For external direct sum, we work in the other direction. We'll start with known representations, and then we glue them together using sum. So for our space, I'll take v direct sum with v prime. Okay, so recall this is just going to be the set of ordered pairs, v prime, where v is in capital V, v prime is in capital V prime. For the vector space structure, okay, we'll add vectors coordinate-wise. For scalar multiplication, we just move the scalar into each coordinate. For the representation, it's the same idea as scalar multiplication. We're going to take our G on the outside, and then we move it to the inside on each coordinate by the corresponding G action. So I'd have pi GV, pi prime G V prime. Now, to visualize this, we first review what happens to linear transformations when we pass to a basis. So let's suppose I have a linear transformation, okay, T carrying a vector space V back to itself. If I want to convert from V to Cm and T to a matrix, what we do is we choose a basis, say E1 through Em. Then I could write each element in our vector space, say V, as a linear combination of the E's, say x1 E1 through xm Em. Now, if we peel off the x's, that's going to give us a vector in Cm, which I call the coordinate vector for V with respect to the basis B. The effect on T, okay, so the recipe for the matrix associated to T with respect to B, what we'll do is we're going to apply T to each basis vector, and then we'll take what comes out and put it in terms of our basis. So those are going to be the columns of the associated matrix for T with respect to B. That'll give us an m by m matrix. Now, when we put this all together, the equation that we use in our work is, if we put T applied to V in terms of the basis, that's going to be the same as taking the associated matrix and then multiplying it by the coordinate vector for V. Then you can decode this to do calculations. Now, if we take all of this and apply it to the linear transformations coming from our representation, in the direct sum what happens, okay, if I put, okay, we'll pick a basis B1 for V, basis B2 for V prime, and I'll put B1 before B2 to get a basis B for the direct sum. Then our picture looks like this. So we'll have square blocks going down the diagonal. Okay, so in the upper left-hand corner, I'll have pi of G with respect to B1. Lower right-hand corner, we have pi prime G with respect to B2. Then we'll have zeros off the diagonals. If pi and pi prime are unitary, so is the direct sum representation using the following natural inner product. So I'll leave it to you to show this is an inner product and that it's invariant under the G action. Next, we have dual vector spaces. So the dual space to V, we denote by V star. That's the set of all linear functionals on our vector space. So we have all linear maps F carrying our vector space V to the complex numbers. For the group action, I'll let G act on a linear functional by passing the group action to the variable with an inverse. Now, the reason I need the inverse is to make sure that the homomorphism property comes out in the right order. So let's take a look at that. So if I let G1 times G2 act on F, okay, that's just going to go to the inside as G1, G2 inverse. If we split that apart, so I'm going to let G1 act on G2 acting on F, what our rule says, whatever mess we have in for the variable, we're just going to take G, put it to the left of that with an inverse. So you can think of there being a box here, and then we're just going to have G inverse before the box. So what do? First, I'm going to move the G1 to the inside with the variable. So I'll have G1 inverse V. When I go to G2, same idea. I pretend that G1 inverse V is in a box. I'm just going to slip G2 inverse in front of it. So I'll have F of G2 inverse, G1 inverse V. Now, if we apply our rule for the inverse of a product, these two expressions are going to match up. So if you left the inverse out, you'll wind up having things in the wrong order. Now, one thing to note, which we'll get to in a little bit, if we consider the G actions on V and V star at the same time. So for instance, if we calculate pi star of G on F on pi G of V, what do? We're going to take the G to the inside as a G inverse. We have G inverse hitting G to cancel out to give the identity. So I'm just left with F of V. So it's like we didn't have the group action in there at all. Now, what happens when we have a unitary representation? We have an inner product. So for dual vectors, okay, we have some linear functional F. There's going to be some W in V. Okay, it'll be unique, such that we can write F as just inner product, okay, variable, comma W. So all linear functionals can be written in this way, but we have to have an inner product available. Now, if we take a look at what the group action does with this representation, okay, of linear functionals, what do? The G passes to the inside, then we write it as an inner product expression, and then the pi G inverse can be pushed to the other side as pi G using unitarity. Now, what's the net effect here? This says that pi star of G is just carrying vectors that look like this to vectors that look like this. So the group action does what we would want. It's just going to be take your vector, wherever it appears, put the G in front of it. Now, this doesn't mean that the representation that we have here is the same as the original. It's going to be off by a conjugate. Let's consider what happens when we choose an orthonormal basis for V. If we choose an orthonormal basis, then if I take the inner product of any two coordinate vectors using the Hermitian inner product for Cm, we get the same answer as if we took the inner product of the original vectors. Now, for the Hermitian inner product of Cm, we could define it in this way. So we know, I could think of vectors in the first coordinate as being our regular vectors in Cm, okay, column vectors. And for vectors in the second slot, okay, we're thinking of these as dual vectors. Since we're taking conjugate transpose, think of these as being row vectors with a conjugate. So that's how I think of our dual vectors. Now, if we interpret our equation for unitarity, okay, we're going to pass to our basis, solve coordinate vectors and associated matrices. We use our definition with the conjugate transpose. Okay, we get this. Then we can rewrite this like this by switching the order here. Now, this matrix product on the inside is going to disappear, which is just the matrix definition of unitarity. Another way to think of this, okay, well, this matrix here, if we let it act on, okay, the element on the left, the dual vector, okay, so this is the action of G on the dual vector, that'll be the same as if we let this act on our elements on the right. So here we're going to act on our regular vectors with an inverse. So this is just agreeing with what we had before. Okay, the action on the dual is to pass to your regular vectors with an inverse. Now, if pi is unitary, okay, we'll have that pi star is also unitary, okay, using the following inner product. Now note here we need this conjugate to make sure that scalars pass in and out of the inner product correctly. Now, the previous board, we noted that the dual representation, was almost equal to the original representation. We're just off by a conjugate. So the dual is going to be equivalent to the complex conjugate representation when we have an invariant Hermitian inner product. Now, formally, we define complex conjugate representation as follows. So I'll have pi bar, v bar. V bar, space is going to be exactly the same as v. We're just going to change the scalar multiplication. So when I multiply by I now, we're just going to be multiplying by minus IV on the original space. For the invariant Hermitian inner product, okay, as with the dual, we're just going to switch the order. That makes sure that scalars go in and out of the inner product correctly. And for the group action, we use the same exact group action on our vector space. For the equivalence, okay, we're just going to define this by taking our vectors in v bar, move them into the second coordinate to get an element of v star. Okay, we say more details about this in a separate video. Next, we have quotient representations. So we'll start with a subrepresentation W inside of V. We'll form the quotient vector space V mod W. Because each pi of G carries W back to itself, we have an action on the quotient. So pi of G is going to send the coset V plus W to pi of GV plus W. Next, okay, here's an important one. We have tensor product representations. Okay, so we say this as V tensor V prime. Now, to begin with, we'll have monomials. So these I write as, okay, little v tensor little v prime, where v is in v prime is in v prime. Then we're going to take linear combinations of these. Now, these linear combinations are going to be subject to the following relations. First, if we multiply one of these monomials by a constant, I'm allowed to pass it to either the first term or the second term, but not both at once. If we have a sum in the first term, I'm allowed to split that up. And if we have a sum in the second term, we're also allowed to split that up as so. Now, if we choose bases, so say I choose a basis E1 through EM for V, F1 through Fn for V prime, then I'll have a basis for the tensor product by taking each monomial E sub I tensor F sub j. So if we do the counting, that means the dimension of the tensor is going to be the product of the dimensions. Okay, also, every tensor product, okay, every element, we could write in this form here. So a linear combination of these elements. For the group action, okay, we're just going to let G act on each component. Okay, so then we extend that linearly to all the tensors. If we have pi and pi prime unitary, then we'll also have unitary representation for the tensor if we use the following inner product. So if we have two monomials, then we're going to take the inner product just on each component and multiply. Then I just extend this using linearity. Some useful examples. If we have V and V prime one-dimensional, then so is the tensor product. So basis element E1 tensor F1. We apply the group action. So I'll move G into each component. Then these are going to be functions from G into C star. So I could treat them as scalars and pull them out in front. Now the net effect here is, if we take the tensor product of two one-dimensional representations, or characters, we're just multiplying two characters to get another character. We could generalize this. So here we'll just assume that dimension of V prime is greater than 1. And I do the same computation. So we move G into each component. In the first part, we have a function from G into C star. And if we treat it as a scalar, I can move it to the second component. Now, if we ignore E1, all I've done is take the action on V prime and just twist it by a scalar. So this construction will be useful later on. One final construction, okay, we have Hom over C from V to V prime. the vector space here is all linear transformations from V to V prime. So first you need to verify that we have a vector space. Once you've done that, we'll have a group action on linear transformations defined as follows. Now, to make sense of this formally, okay, we have two group actions, one on V, one on V prime. How do we work those into a linear transformation? Now, our domain variable is V, so if I want to push G into the domain, okay, acting on the domain variable, we've seen from working with the dual space, I want to move G in as G inverse. So that way the homomorphism property comes out right. So, first step is that we're going to have pi of G inverse on the inside. Now, we have a group action from V prime. Okay, so if we're working with V prime equal to C, we're just going to have the dual space. Well, note, if I put an element from V in here, L is going to send it to an element of V prime. Then I can apply pi prime of G. So we're going to put pi prime of G on the outside. So that's our group action formally. Now, this actually arises nicely if we track out the isomorphisms. So we're going to have a vector space isomorphism between Hom and the tensor product of the dual of V with V prime. Now, going from right to left, okay, if I take a linear combination of monomial tensors, I could send these to a linear transformation defined as follows. Then you would need to show, first, that this map is linear, then that it's an isomorphism, then finally, I want that the natural group action over here corresponds to our group action defined as so. With that, we'll have an equivalence of these two representations. Now, if we have pi and pi prime unitary, then this group action here will also be unitary with respect to the following inner product. For this inner product, okay, let's review how we define the adjoint of a linear transformation. So we're assuming I have a linear transformation L carrying V to V prime. The adjoint of L is going to carry V prime back to V. L star, the adjoint of L, is going to be defined uniquely by this equation here. Okay, so note, if V is in V, L of V is going to be in V prime, and this makes sense. On this side, L star of W prime is going to carry, okay, this is in V prime, so this is going to be in V, and then this makes sense. Now, with that, our inner product for two linear transformations, say L1 and L2, is going to be the trace of L1 times the adjoint of L2. Now, you need to verify that this is an inner product, okay, a Hermitian inner product, and that it's invariant under our group action. A final note on the definition of the inner product. So if we compose L1 with the adjoint of L2, okay, we're going to go from V prime to V, and then from V to V prime. So we're going to go from V prime to V prime, and it makes sense to take the trace. Note, this will work if we switch the order also. Then we'd be going from V back to V. To finish, exercises. First, I want to verify all group actions in 1 through 5. So this is just verifying the homomorphism properties. Then, where we have equivalences in 1 through 5, you should verify those. So you want to show that you have a vector space isomorphism, then that isomorphism is an intertwining operator. Finally, I want to verify unitarity in all cases in 1 through 5. So where we have inner products, you want to verify that the group action preserves them. Another exercise. Okay, we'll assume that we have pi V unitary. We're going to have W inside of V as a subrepresentation. So W is just going to be a subspace that's carried back to itself by all pi of G. We want to show the orthogonal projection, PW, carrying V to W is an intertwining operator. And then with that, we want to show that the quotient representation on V mod W is equivalent to the orthogonal complement of W as G representations.